So now we're moving from 1D optimization, dichotomous search and golden section search, to 2D optimization. And 2D optimization is really the basis of multi-dimensional optimization that you use in many real world applications. And we're going to consider ultimately how we can minimize typical 2D quadratic function using iterative methods. But before then, we need to establish that a minimum exists. In order to do that, we need to construct a two-dimensional or multi-dimensional Taylor series, and then we'll notice that within that Taylor series there's some object, some matrix called the Hessian, which will be very key to establishing whether a global minimum exists. So I'll now hand over to the theory. Okay, so we're now looking at the multi-dimensional equivalent of f double prime. So what we need to look at is basically called the multi-dimensional Taylor series. And a definition first is called an inner product, which essentially is the dot product, but it's a more general way of doing things with vectors that allows other types of definition to appear. So, and it's also quite compact. So we consider two vectors, x and y. And the inner product is written down as x transpose y, and it's the same as x dot y. So we'll be using that notation throughout inner product. So when you see an x transpose y, that's an inner product. What we're going to do is we're going to consider in a general vector space. So you have your minimum is given by a vector x star that could be of any dimension, and then we consider a deviation, and we're going to call it s vector. That's a deviation from minimum. And if x star is a global minimum, f will increase in all for all s. So basically we're just generalizing our expression with global minimum, and you were saying if as we perturb a deviation s in any direction, then f should increase in all directions. So that's the sort of framework we're working with, this multi-dimensional framework. Another bit of notation, we can write f, a function of a vector, if f x is just a vector xy with components, scalar components x and y, is equivalent to writing f of x and y. And you see already that being able to put a vector in the arguments of a function is very convenient, especially when you've got more than 2 dimensions, 10 dimensions say, you just put the vector in there. So that's another bit of notation we'll be using. So it's okay to put a vector in the argument of a function, it's equivalent. So we're then going to write down a multi-dimensional Taylor series. Basically, we want to write down f of our minimum point, x star, plus our deviation s equals a whole bunch of things, and it needs to more than one line of the board. So you have f of x star, that's the function value at the minimum. Then all the bits you have in a normal Taylor series, but now they're expanded over. So S is n dimensions, by the way. I'm going to use that. So we have the first derivative, so we're going to then sum over SI, so SI are the components of S, times the first derivative evaluated x star. And then we have the second derivative bit, a little bit more complicated because it's two summations. So I equals 1 to n, j equals 1 to n, si, sj. So these are our, again, components of S. So remember, our S vector is simply S1, S2, all the way up to Sn transposed. That's what our S vector is. So the components of Si and Sn are there. We have our second derivative, dxi dxj, plus higher order parts. So a little bit more to digest here now, but it still is your Taylor series. In fact, if I set n equals 1 into this, it would just reduce down to your standard one-dimensional Taylor series that you're all familiar with, yeah. But we're going to consider n is 2 mainly, two-dimensional problem mainly. So you have the first derivative bit, and then you have the second derivative. And the reason we have a summation of 2 here is we're trying to include all the derivatives. So the say in 2 dimensions, d2f by dx squared, d2f by dy squared, and all the cross derivatives. So that's why we have this double summation here. It includes all the derivatives that arise when you go into more than one dimension. And don't forget, we've got that factor of half that you have in your standard Taylor series. And so that's a general multi-dimensional form. Now we're quickly going to move to the specific case of consider n equals 2, 2D case. And that's really where a lot of our examples are, and where we're going to focus on learning, mainly because you capture the essence of multi-dimensional problems in 2D. You don't in 1D, so that's the sort of simplest case that we can think of. Okay, we're going to then also define something that bundles together the second derivative, basically what's called a quadratic form. And sometimes these come up in pure courses sometimes, so they tell me. And it's a function of the S, and basically we're going to basically bundle all the this fairly involved double summation that came up in previously. Into a single quantity Q. That's the first thing we're going to do. So bundle everything into this quadratic form. That's going to make it easier to interpret. Okay, so that's just a number. Basically, this is our. Notice it's a second derivative without the 2 half factor, just the way it's qualified. And then we realise that at the minimum, or any extreme, the first derivative is 0, yeah, which is the case So this radically simplifies the presentation of this Taylor series. With the first, all the terms in the first derivative are just 0. Okay, and we're going to bundle all the second derivatives into this Q. Then we can rewrite our multi-dimensional Taylor series just me checking the time there, by the way, into a simple expression now where you have the value of the function at the minimum. The first derivative is 0 because we're at the minimum, plus this Q quantity. And of course the half factor wasn't included in its definition, so it comes in there. And why have we done this? Well, remember we had this sort of a little sketch that I drew at the beginning where if we have a global minimum, what we're saying is that the function will increase for all values of s, so any values of s. And what it's saying there is you've got the function at the minimum and this deviation of the function at the minimum. So if this thing is positive for all values of s, then the function is the next star is at the global minimum. So we observe then if q of s is greater than 0 for all s, okay, not equal to 0. Pure mathematician told me to put that on one day. Okay, very much improve the rigorousness of my presentation here. Basically, so that q is greater than 0 for all values of s, so that's basically saying, you know, you're starting at your point x star, which is your minimum, and you're sort of searching, if you like, that's why it's called s actually, in any direction. And if the function increases in any direction, so q is s greater than 0 for any s or all s, then f will increase. So if q, then x star is a f of x star is a global minimum. Okay, so the question then is well, we've just bundled the second derivative. We haven't yet actually explicitly computed what q is. Can we now compute it for a two-dimensional case and see what it means in terms of the function? So how do we relate the function to this quadratic form? This quadratic form is very useful for just summarizing what's going on, but let's see if we can now compute things. So when n equals 2, then our search vector is just a two-component vector, given that. And then our q of s, which was a summation over I is 1 to n, but of course n now is 2, and then j equals 1 to m, which is 2, si sj d2 f dx I dxj. So this is quite cumbersome to write down, but all it is saying is, you know, it's a second derivative. When I equals j is 1, then that's just d2f by dx squared. Okay, it's just a very compact way of concluding all the derivatives in s. So that's exactly what we're going to do now. We're going to expand out this expression. So when I equals 1 and j equals 1, when I is 1, j is 2, I is 2, j is 1, and let's see if I can put it in the end of the line, plus S2 D2F dy squared. Right, let's just clarify what I've done there. So we've got a summation from 1 to 2 and another summation from 1 to 2. So we've got basically 4 options for I and j. Let's just annotate what we've got here. We've got I equals j is 1 for that one. And then let's just write the other one, which is I equals j is 2. And then you have the in-between values, which is I equals 1, j equals 2, I equals 2, j equals 1. And of course the x1 is simply x, x2 is simply y. Yeah, let's just write that out. So x1 is x, x2 is y in that notation. Doing that, you fit it all together. So we've summarized a lot of terms here, and written out. And in fact, this is where matrices come back in again, because actually it turns out a more compact way to write down this so-called quadratic form is in matrices. Okay. Using a matrix, and so Q of S is, this is where my definitions of inner products are going to come in. So we do basically a product of 3 things. We're going to have a vector times a matrix times a vector. So if that makes sense now, because we've got this idea of an inner product. We have S1, S2 is our vector here, and S1, S2 the vector here. So we had 4 terms before, and we've got a 2 by 2 matrix, and each of these is going to be the coefficients on the terms in that previous expansion. So in the diagonal, we have d2f by dx squared, d2f by dy squared. Let's see how that works. So the way to think about it is work from right to left with this. So first of all, multiply d2f squared by s1, and then pre-multiply it again by s1. Gives the s1 squared term. Equally the s2, d2f by squared at s2, and s2 squared term. So this is where this idea of a sort of inner product, which is essentially a dot product, but we're writing it down. Remember, we wrote down it's the vector transposed times the vector. So, and then we have cross terms appear on the off diagonal. And those who observe, if f is a continuous differentiable function, these 2 cross derivatives are going to be the same. So we're actually going to get a matrix which is called symmetric, i.e. that it's the same either side of the diagonal. So let me just give you a few examples of how this relates to those terms before. So you have S1, you pre-multiply by that term, so that term will multiply by S1, that term will S1, that will then give you this S1 squared d2f by dx squared, which is one of the terms we had before, yeah? Yeah, so that's one example. Let's just undo it again. Now, if you let's just consider S2 times in the matrix multiplication, and those will then give you d2f by dxy times s1, that's the first bit there, times s2. So you can see now how these cross terms arise. So this presentation is new to you, but now we've sort of defined this idea of that inner product is just your dot product. All we're doing, another a way to do it. Let me undo that. All we're doing is multiplying a matrix by a vector to give a vector, and then dot producting it, if you like, with the outside vector. That's if you prefer to think of it that way. Okay, so this is very useful. So actually, what we can write this down as is that Q of S is S vector transposed times something called H and S. So we just call this vector H, and H stands for Hessian. Is the Hessian matrix. So you come across these sort of key matrices that contain all the derivatives. You can probably come across a Jacobian before, which is something that contains first derivatives of two functions. Here we have one function, but we have all the second derivatives in 2 dimensions. That gives us another 2 by 2 matrix. So it's called the Hessian, and it's something you need to remember, but it's not too hard to remember. In 2D, you just the simplest way is to fill in the diagonal first with just the second derivatives, and then the cross derivatives go in the off diagonal places. And that's enough for this little video. The key question is, we've had this result, Q of S is greater than 0 for a global minimum. Which is our quadratic form. How is this related to H? So Q of S, which has got all our derivatives, which we can compute. So what do we then need to do to H to satisfy this global minimum property? So I'll leave you to think about that. Of course, you can just look ahead in the lecture notes if you want to find the answer, just read ahead. Okay, see you next time.